video, we're going to take a look at the hydrolysis of an ester under basic conditions. And this reaction is also known as saponification. So this is related to the fact that this is the reaction that can be used to make soap. So soap is made by the base catalyzed, or base promoted, I should say, hydrolysis of long chain fatty acids, and that makes soap. So kind of a cool story. All right, so if we take a look at this reaction, we're going to draw just the general structure of an ester. So here is an ester, and so if we're doing this reaction under base promoted conditions, and we say promoted rather than catalyzed because the base is not a catalyst in this reaction, it's actually consumed during the reaction. So if we're going to get the carboxylic acid, we usually do this as a two-step process. So we're first going to react to this with aqueous base. And this reaction will work even if you don't heat it up. It'll just be slower. So most of the time we will see heat being added. So we'll say usually. But if you don't see that, don't let that throw you off. The reaction will still occur, just again, a little bit slower. So that's the first step. And then the second step, because it's done in basic conditions, you're not actually going to have a carboxylic acid upon hydrolysis. You're going to have the carboxylate, the anion. So we usually add a workup step to neutralize the reaction mixture when we're done. And so what that'll do is we're basically cleaving here, and you're going to make a carboxylic acid and an alcohol, right? So this portion here will become your carboxylic acid. And this other portion of the molecule here will become the alcohol once we cleave this. So we will get the carboxylic acid, right? So there's that carbonyl and whatever that R group is, and then we're going to add the OH. And so that OH is coming from your hydroxide. So that is where that's coming from. Okay. And then you're also going to liberate this side of the molecule as the alcohol. So we're getting that carboxylic acid and the alcohol. So let's look at a specific example. We'll actually fill in some groups for both of those R groups and run through the mechanism. So these base promoted mechanisms are always shorter than the acid catalyzed. And so that's because we just don't have as many proton transfer steps. So it's kind of nice that way. So let's say we start with, okay, we'll just leave it there. So we're going to start with ethyl benzoate. Right, so the first thing we could practice is predicting what the products are going to be, right? So we see, okay, this is going to be our carboxylic acid portion, right? And then whatever was attached to that, so that is the ethyl portion with the oxygen there, is going to become the alcohol. So we can hopefully predict the product pretty quickly. So two-step process here. We're going to use sodium hydroxide. We'll say we're going to heat it up. And then just an aqueous workup to make sure we get the carboxylic acid as the neutral carboxylic acid and not the negatively charged carboxylate anion. So there's our carboxylic acid and the alcohol. So let's take a look at the mechanism for this. So under base promoted conditions, you have a really good nucleophile. And so what the first thing it's going to do is that really good nucleophile is going to attack your carbonyl carbon, right? So there is our ethyl benzoate, and our good nucleophile is that hydroxide ion. And so that is going to attack the carbonyl carbon, which pushes electrons up onto the carbonyl oxygen. And so this is going to give you a tetrahedral intermediate, and we're saying this is reversible because it is. It could easily go backwards. Okay, and let's look at the tetrahedral intermediate to see why that is the case. So we've got that negatively charged oxygen, you have the O ethyl group, and then you have the hydroxide that you added. And so the reason why this is reversible and could go backwards is that the leaving group abilities of these two groups is approximately the same. Okay, But when we're drawing a mechanism, we're going to concentrate on drawing the reaction in the forward direction. So we are going to draw the reaction where this tetrahedral intermediate, so let's label this as a tetrahedral intermediate. Is going to collapse. So this is a familiar pattern with our carboxylic acid derivatives. We're going to reform that pi bond and kick off the leaving group. Okay, and so again at this point still reversible. Right? So we have formed the carboxylic acid actually, and so you might be really tempted to stop here, and the alkoxide. The problem is why you can't just stop here in the mechanism is that this is a base and this is an acid, right? And you might also still have hydroxide around. So either hydroxide or this ethoxide, whichever one gets there first, is going to immediately remove that acidic proton. And you cannot stop this reaction from happening. This is just acid-base equilibria. And I say equilibria, but really there's such a difference in pKa values that this is gonna go forward. So this is gonna give you the carboxylate and I chose to use the ethoxide as my base just to conveniently get that ethanol. Again, it could, but depending on how much hydroxide you have in your solution, you could easily draw this with hydroxide as well, and I don't think that you would be wrong. It's just whatever base is going to get there first. All right, and so this would be the products. And so I didn't draw this as an equilibrium error. We could, but it's really not going back that far, and that's because you have a large pKa difference between an alcohol and a carboxylic acid. So this will be the product of the first step, and here it's going to stay until you add in that second step. So that's that. This is an acid workup step. And so you'll often see this with basic reactions that you need to put a proton back on. So that's where you add in this H3O+. So we'll just draw it in here so that we can protonate this alkoxide and get the neutral carboxylic acid as the final product.